Test check, mic check, all good. Hello, I'm Luis Ramirez, founder and CEO of Mawari. And at Mawari, what we do is basically we deliver the Metaverse. For you that are actually old enough to remember how painful it was to download content on the internet,
Cool.
well, Mawari's mission is to prevent that from happening for the Metaverse. So it took actually more than 20 years to build the current infrastructure that powers the internet. Like, for example, you press play today on Netflix, and you have immediate access to the movie without having to download it. And users actually give this for granted. This infrastructure is invisible to them. And now in the industry, we're talking about the Metaverse and how great it will be. And that is this ever-persistent, real-time 3D digital twin of the real world, blending the digital and physical. You call it all the words. But what few people realize is that actually the amount of data that this takes and the amount of computing power that this takes is not here today. So the infrastructure that we need to really power the real world Metaverse is light years away from what we have today. So this is what we call the elephant in the room and the problem that we're solving. The reality is that today's technology stack is not compatible with interactive 3D content delivery at scale. This is for many reasons, many technical bottlenecks. First of all, we have the content size. When we talk about 3D content, we're talking about gigabytes, terabytes of content, and then when you go talk into web, okay, so we need to optimize the assets, and it's a very long process pipeline. Secondly, the content format. So until today, we've seen 3D content in movies, in video games, everywhere. However, it has been always delivered to a 2D screen. So when we talk about the next generation of content, which is with XR devices, smart glasses or VR headsets, the data technically needs to stay in 3D so that you can do all the spatial computations and put the content in context. So this also doesn't exist today. There are no standards. So we need a new data format and a new way of content delivery. Lastly, the devices have very limited processing power. And here we're talking that even though smartphones are getting better and better and better, I mean, the amount of power that we need to process a photorealistic digital human, it can only be powered by NVIDIA GPUs that are on the server or in a gaming PC. So actually, if you try to do something with the smart glasses that is actually a little bit more quality than the usual, then the devices start overheating. And then on top of that, if you add 5G to the mix, then it's a killer combination. The device is really just, the battery dies. And as a matter of fact, there are some rumors that Apple have been delaying the release of their headset for that specific reason, because they're trying to put the M1 into your head. But if it's going to burn, you will have a tan every day. So, so it doesn't make sense, right? So this is what Mawari is doing. We're breaking these bottlenecks by rendering the content in the cloud and streaming it to mobile XR devices, enabling immediate experiences enabling immediate access to unlimited XR experiences. We have a 3D streaming codec that reduces the network bandwidth up to 100 times. Think about like what MP3 did to the music industry. We had the WAV files. Then once the MP3 was born, then we started distributing the music in the peer-to-peer networks, and later that led to streaming music and Spotify and all these services. Second, as I mentioned, the format is an issue. The current state of the industry, we are streaming video, and we're trying to fit video into XR devices. For VR, it may work, but actually with AR, you need to do occlusion and other complex operations. So if you have a 2D overlay, it's very difficult to then do all this, because in a way, you already pre-rendered the content on the cloud. So we created this framework in which we stream the geometry. So we do compression on the server side. And then on the client side, we also do decoding of our format, but in a very light way so that XR devices can actually display the content, but at much higher quality. Lastly, we're working with the telcos and building this cloud rendering network that enables edge computing with very low latency and interactivity. So how does it work at a very high level? We have the XR platforms, the content creators on the left, and via our XDN, it delivers the content in real time to the users. So these are our main product features. Object streaming, so this is the main approach about geometric streaming, that instead of streaming the full scene, in your virtual world on the server side, whether it's Unreal Engine or Unity, you can select what objects to stream. And this immediately, when you are on the client side on your application, allows to do occlusion. So for example, right now we're working with T-Mobile and the Snapdragon Spaces program. And since the Snapdragon actually allows the depth API, so actually we can finally occlude content for AR glasses. Dynamic stream support is that even though you are still running the application, you can change between streams. So this, for example, previous examples of this is dynamic streaming of advertising and so on. And lastly, split rendering, in which we use the device and the cloud in the most efficient way. So and this prevents the latency. Because for example, let's imagine that you are running your application at the normal runtime of the device, and it's less than 10 milliseconds of latency. So if you have all the environments and UI rendered locally on the device, but then as a plugin, you insert cloud render content, then even if there's a network lag, and when you're moving your head, it is compensated because your brain is actually thinking, okay, I'm seeing the locally rendered content, but the cloud rendered content then suddenly catches up, and it looks like a very smooth experience. Because this is one of the big issues today with cloud rendering. It's like, okay, so if there's no edge and if there's no good connection, you cannot achieve the latency required to not give you the motion sickness. So by doing a split rendering, we prevent the motion sickness. So here's a quick demo of all the things that we've done. And after this, I will present case studies one by one. OK, this was supposed to have sound, but I will describe it. OK, so for example, this car has more than 4 million polygons, 4K textures, real-time reflections. This is a metahuman from Epic Games connected to an AI backend, and we can stream it seamlessly to mobile devices and XR devices. So, okay, let's move on. So, what is our core technology? This patent-pending 3D streaming codec that reduces the bandwidth up to 100x. This is compared to uncompressed volumetric videos. So we offer a similar, like MP3, like similar fidelity to uncompressed volumetric video, but at 100x of the costing bandwidth. And lastly, the power consumption is a very lightweight format. Just imagine if you have an NVIDIA GPU inside your smartphone. In terms of the traction, the company has been called the Akamai of the XR Cloud, the MP3 of AR by AR Insider. I think Mike Boland is around here. And also the $20 billion codec. Our mission is to enable the metaverse. Also, Newzoo has identified us as one of the early architects and pioneers of the metaverse. And I can proudly say that we are the only, in this diagram, we're the only XR-focused streaming solution. So let's go into the case studies. The first one is in collaboration with the KDDI, AWS Wavelength, and Inmersal and Starfy. So here the main point is that we achieved to implement the full horizontal stack of technologies needed to create a realistic AR experience. What does this mean? We integrated the SDKs from Inmersal, from Starfy, into a smooth, seamless indoor and outdoor mapping experience, while at the same time streaming the digital human and doing this split rendering between the embedded content in the space. All this in the edge computing in Tokyo using AWS Wavelength servers. So let's have a look.
Hello, I am Aiko. Please let me introduce you the latest collaboration between KDDI and Mawari, powered by AWS, Starfy Outdoor Visual Positioning System and Immersal Indoor Visual Positioning System. These technologies are integrated into one application delivered by the powerful and ultra-low latency AWS Wavelength service. Hello, my name is Aiko. We are in Ginza, which is located in the center of Tokyo. This application leverages the robust and superior performance of the AU 5G network. This service allows me to provide you with visual and seamless guidance both outdoors and indoors. Welcome to Ginza Yangoroku, created by KDDI. Go straight till the end of the hallway and you will find the stairs.
Okay, so all these videos that you will see are actually recorded from the smartphone or the smart glasses. It's actually the live output. And yeah, I just want to say that it's very useful to have digital humans because they replace my talking and I can take water. So next, yeah, the next project is more about sustainable fashion design. Okay, so in Japan, there's a lot of the trend about digital transformation of the industry. So the challenge here was, okay, so let's just design clothing in 3D without wasting resources. But the fashion designers needed ultra-realistic quality to really tell, okay, this is how I really want the dress to look or not. So what we implemented is by cloud rendering and streaming again in real smart glasses and also in 2D display, this real-time streaming. So you will be able to see it here. It was actually, it was actually in the news in Japan. Sorry, but the text will be in Japanese, but you will get a
ファッション産業の環境負荷を減らそうと異業種も動き出しています。
よろしくお願いします。
大手通信会社などが開発したのは AR 拡張現実の技術を活用した装置です。
メガネをかけて。
So you can see here, it's in full scale, ultra realistic, this digital human and real-time physics,
商品
everything
開発の段階で使うことを
streamed
想
to the
定、
smart glasses.
データをもとに仮想で試作品を検討します。
表面のそのちょっとモコモコした感じが
And this
非
is
常によ
how
くわか
the
る。
fashion
しかも
designers
近づくことができるからその
technically
質感がリアルにわかります。
preview this in real time
この技術を
and
使うと
modify the design until it's ready to go
環
into
境
real
配慮どんないい
manufacture.
ことがあるんですか。完成品
Okay, let's go to the next case study. This is a collaboration with KDDI, Deutsche Telekom, again, Starfy and MobileJX. Here it's a little bit similar. It is about outdoor mapping, but here the main point, and what very few people know, is that the 5G configurations, edge computing configurations vary from company to company and even from country to country. So it's not easy to just have one application that fits all. Like let's say you release your application and it magically works in Germany and in Japan. It is not that way, so this was a challenge and part of our content delivery network service in which we standardize this for developers so that they can just bother on or focus on creating content rather than trying to find the right configuration for each edge server computing. So this application, in a nutshell, has two digital humans. One of them is German, westernized, speaking in German, and the other one is from Japan, speaking in Japanese. So it's a highly localized application, but it runs smoothly in both countries and communicating with the two telcos. So let's take a look. Also, this video has a kind of like a good explanation about the power of cloud rendering. So let's take a look.
1日に330万人が利用していて、駅利用者数で世界ナンバー2です。カルチャー、ファッション、繁華街の中心地として日本屈指の
By the way, I forgot to say this is a multiplayer experience, so actually we have two cloud rendering instances synchronized, so every user can see their content in their own point of view.
This trial tested the ability to run advanced edge-enabled services across different geographies and operator networks. Using the MobileEdge X-Edge cloud platform to provide unified access to KDDI's and Deutsche Telekom's 5G Edge MEC resources, Starfy and Mawari were able to easily deploy their services and run them with optimal latency and bandwidth to create an outstanding user experience. Leveraging Mawari's XR streaming solution, we were able to deliver a multiplayer real-time experience featuring hyper-realistic personalized digital assistants and sci-fi billboard advertisements perfectly placed into the real world outside in the streets thanks to Starfy's visual positioning system. All working in perfect synchrony and speed thanks to MEC and 5G. Let's dive into the advantages of edge computing with an A/B comparison. The digital human on the left is rendered by a smartphone and the one on the right is rendered by a MEC server. The difference in quality is evident. The MEC server digital human comprises hyper-detailed face animations, high-quality textures and high polygon count, ultra-realistic hair and clothing simulations, complicated lighting scenarios with dynamic materials and reflections. This can't be accomplished with a smartphone GPU today. In addition, to render the digital human on the left, more than 1 GB of data needs to be downloaded, forcing users to wait and providing a bad user experience. In contrast, the one on the right can be streamed instantaneously. We will continue to work with interested operators and developers to build a global platform to make access to MEC infrastructure as easy as possible.
Okay, thank you. Then the next one is an art gallery. Here's also a digital assistant, but this is from Unreal glasses. Here the point is image recognition, so the application knows exactly where you are in the museum, and then the digital human appears and explains in context about the painting. So here, she says welcome. So this is directly from the viewport of Unreal. So the application guides you and tells you, okay, let's go to this painting. Then she appears and she starts explaining. Next picture, and then there's also a quite interesting experience right after these pictures. So here you will see this based by Emile Gallet. I mean, it's actually 16K textures. It's a very heavy asset in terms of photogrammetry. So what we did is to make it 7 times of the real size. The users will never have the chance to touch it or even get this close. So you can observe it with the smart glasses, all the details, all the textures, and even just go inside, which is a new experience that XR allows that it didn't happen before. There you go. So kind of like a VR. It looks like VR because of this limited field of view of Unreal. So, okay, let's do this last one because we're running out of time and I would like to have some Q&A time. So this is a collaboration with Kohei Inawa, which you may or may not know. He's like the new Murakami of Japan. This is a live installation that actually has been extended to the end of October in Japan, more than 1 year. It's a consumer-facing application. And here, the main point, this statue is hanging from the ceiling. And we got the challenge, okay, so the artists say, well, I want to embed like some point cloud dance going around this statue, can you make it happen? And basically, what we ended up is like, okay, he created a full 3-minute performance of an Alembic file of 200K points. And guess what? It was like 45 gigabytes. So obviously, a smartphone or not even a powerful computer can actually render this in real time. So with our compression algorithm, we were able to reduce it to 400 megabytes and actually stream it to iPhones. And on top of that, these points have real-time reflections and textures. So you will see it's very beautiful. So if you have the chance to go to Tokyo, now I think from this month they will open the doors to tourists. It's worth watching it. So that's how the statue looks like. Get your smartphone, open the application. Detect the location. Then you start the experience, and then the indoor mapping works, and you will see how we were able to run this experience streamed at actually at the 30 frames per second, because even on the server side, it was very hard to achieve the 60 frames per second because it was a super heavy computation. But as you can see, each point has textures. It's the textures of a rock, and it's a reflective material. And all this is perfectly paced, so you can watch it from any point of the shopping mall. On top of that, also very ambitious related to this project, all the dancers. Right now you're seeing it because of the video in lower frame rate. All these are actually real humans dance with, recorded with depth cameras. So it's a really beautiful project. Okay, I ran out of time. I have a lot more projects to talk about, but yeah, let's start with the Q&A. Thank you.
Hello, my question is, you mentioned that for the last demo, you have, as the original point cloud is 200K, right? Then after the compression, how many points you have?
It's the same, it's 200K, same? Yes.
So it's still keep 200K point for a person?
Yes, because our codec rearranges geometry in a special way to stream it in a lightweight. Okay, so it's still one-to-one.
Okay, so then what's the latency for this application?
Latencies. Okay, with operators, we benchmark up to 10 milliseconds of latency. But as I explained, with the split rendering, you can compensate the latency. So for example, if you get 30, 60 milliseconds, it still looks real. So for example, of course, it's good to run everything at 60 frames per second. But if you do half and you do 32 milliseconds, that is still acceptable, and it will look like a really smooth experience.
Okay, thank you.
Yeah, I think you probably answered that, but I'd like to confirm. Sounds like you don't touch the architecture of 5G, but just the algorithm of your compression technology. You don't need to increase the bandwidth of the whole transport system, but your innovation is purely with the compression part. Is that true?
It is true, but it's true that we optimize the bandwidth, and that's a big benefit even with 5G, because in the end we still need a low latency. Right now, also, we're collaborating with T-Mobile. Like, for example, if we have APIs from the 5G network and to do like dynamic bandwidth, that will help. But right now, we are just at a very early phase where we're starting to explore this with operators, like what kind of data we can get from the network, so that we can even optimize more the delivery.
Okay, thanks.
A very similar question on that. So what is the data rate that you require in the downlink with this compression?
Right now, we're benchmarking, like ideal is 10 to 15 megabits per second, but we can go as low as 5. And the better, like almost lossless quality would be from 20 to 40 megabits per second, depending on the type of content, but also how dynamic it is. Because it's a more static content, of course, we stream just the difference, so this is more dynamic, so we reduce the bandwidth. So it's not always a constant bit rate.
Okay, thank you.
Hi, thank you for bringing the elephant into the room. So one question, you mentioned MEC. Can you describe a bit more about MEC?
MEC.
In this context that you have used the solution in?
Well, for low latency, we need to be inside of the operator's network, and they bring this proximity to the user. So for example, AWS has this wavelength version in which they work with operators to have the GPU service close to the users. So that's where it takes place. Because, for example, we benchmark one-to-one AWS on a normal zone in Tokyo versus the wavelength. And with wavelength, we got 10 milliseconds of latency, and with the normal zone, it was 32. So that's how it helps.
So the MEC in this case is AWS wavelength. So
yes,
okay,
and also that provides a very powerful server to render good content. Well, if you're a developer and want to try our solution, feel free to talk to me. I mean, we're looking for developers that are really looking into the next generation of content. Thank you.